Okay, kids. If I seem a little bit frantic and I might have forgot some stuff that I need to set up, it's because we had a staff meeting this morning that I just got out of, so I'm a little disheveled this morning and I'm not sure that I have all my ducks in a row, but we'll get there. Okay, on a random question, so here, I'm gonna try and figure out like a new way to maybe like get your papers turned into me. And so right now you all email it to me and then I upload it and then I grade it and then I send it back to you guys as an email. Okay, and it's a little bit of a process. But we think we might have found a way to do it through like Google Classroom, where you would send it to me as it would still be the same process on your end. Okay, you would still take a picture of it, you would still with Cam Scanner, but instead of sending it to me as an email, you all would upload it into Google Classroom. So would you, how's your, and I've got to figure out the mechanics of it on my end because I've never used Google Classroom because I really don't like it, but it might save me some steps because if you could upload it into Google Classroom, I think I would have the capacity to like open it in Google Classroom, write on it, and then save it in Google Classroom without sending it back to you guys as an email and everything else. It will save me a step. So what would your comfort level be uploading stuff into Google Classroom? Would I have to like start over from scratch, or would you guys know what was going on?
I would know what's going on because I do that for my pre-calc class anyway.
So that you uploaded into Google Classroom anyway, like a Cam Scanner or
Yeah.
You already do it that way for your pre-calc.
Yeah.
Okay. What? Anybody else? Would I have to start over from scratch, or what? I'm just trying to figure out if I can do this, what I would have to get out to you guys in terms of a procedure. Sproles, what are your thoughts?
I'm indifferent about it.
But here's the point. Could you do it if I said, hey, you need to upload it into Google Classroom? Is that something that you could handle?
Yeah.
Okay. All right. Well, I'm not saying I'm not going to change right now, but that was one of the things that we talked about in this meeting that I just got out of, and so that's kind of where I'm thinking about. Okay. I just wanted to kind of get a feel for that process. Okay. So let's talk about the assignment from yesterday. Anything? Well, we already have some up on the chat box. Hold on, let's see what's in the chat box. Raina, you know what's going on. Hannah, we use it for other classes too. Okay, fantastic. All right. So, any questions that you want me to go over on the assignment?
Can we go over number 7 for again?
Yeah, we can. So, is that with the bullet and the block, and you're trying to find the new velocity of the block?
It's how fast is it moving when the bullet leaves?
Yeah, okay. Okay. So here's your setup on all of these problems. Start with the basic idea of what you have. So, oh, I can start that up camera. Hold on. Okay. All right, we're good. Want to make sure that other camera is going. So, you got two things. You got the momentum of the bullet plus the momentum of the block equals the new momentum of the bullet plus the new momentum of the block. Start every one of these problems with this idea. Okay? Now, so here's what's going to happen. The block is at rest, so you don't have to worry about that. That's gone. It's not part of the part of it. Now, over here, these two aren't moving at the same speed, okay? Because of the fact that the bullet passes through, right? Now, what you'll see on number 7 is that the bullet slows down. The bullet goes from 475 meters per second down to 275 meters per second. So this is going to be the mass of the bullet times the velocity of the bullet, the mass of the bullet times the new velocity of the bullet, plus the mass of the block times the new velocity of the block, okay? So, here's your setup. You know everything except for the new velocity of the block. So what I would do is I would subtract this over and go, okay, this is going to be the mass of the bullet, velocity of the bullet, minus the mass of the bullet, the new velocity of the bullet, divided by the mass of the block, and that's going to get me the new velocity of the block. Now, if you really wanted to get fancy here, you can factor out like the mass of the bullet, and then you're just left with the velocity of the bullet minus v prime times the velocity times the mass of the bullet if you wanted to factor that out. But if all goes well on number 7, you're going to get a not so good GPA. Okay? And the other thing is that think of this in terms of your answer. Your answer on number 7 has to be a positive value, because here's the block, here's the bullet, right? It's going to hit, and the bullet's going to keep going through, but it's going to lose some of that momentum. So there's no way the bullet's going to pass through the block and you end up with a negative velocity for the block, where it's going to be going in the opposite direction. Okay? Now, let me talk about number 10, or at least kind of get you started on number 10. Okay? I did hear about number 10. All right. Ooh, we got a whole bunch. All right, so 10 and 11. All right. So here's the deal. So let's go 10, then we'll do 11, then we'll jump back up. Okay? So on number 10, here's this frictionless inclined plane, and that's going to be at a 30-degree angle. So here's, and this is, I kind of threw this in because you kind of had to go old school on this one. So I was nice and I made it frictionless. So you're going to find that force parallel using Fg sine theta, okay? Now, that's the only force acting on that mass, okay? That's it. There's no friction, there's nothing else. That's the only thing that's going to make that thing move. So you need to find your force parallel using Fg sine theta. You already have the weight of the block. Now, you're going to need the mass of the block later on when you find the momentum. So take the weight of the blocks, divide that by 9.8 meters per second squared. That's going to be your mass. So at the end of the day, this force parallel, which is Fg sine theta, is going to equal the net force, which is going to be mass times your acceleration. So find the mass of this block by taking the weight of it and dividing it by 9.8. That's going to get you the mass of this block. Take your force parallel, divide that by that mass, there's your acceleration. Once you get your acceleration, then you're going to use that equation. So there's a whole bunch of steps that you need to do for 10A. Now, if 10A is wrong, everything else is going to be wrong on this problem. So your answer to 10A should be 3.13 meters per second. Okay? Because literally, if that is wrong, every answer that you're going to have from there on out is going to be wrong. Okay? So, find your net force, find your acceleration. Now, and don't be stupid, okay? I beg of you. Make sure that you can find this value. Just don't write it down, okay? Don't just write it down and go, oh, I got the answer. No. Because on the test, guess what? I'm not going to tell you exactly how to do the problem, and then I'm not going to say, oh, here's your exact answer. Okay. Now, on B, you have the block sitting down here. They're going to move off together, kind of do the California thing. Okay? So, obviously, your velocity on B has to be less than your answer to A because you've increased the mass. Okay? So your answer to 10B is going to be around 1-ish meters per second. Okay? It's an ish, but it's going to be around 1. Now, when you get to C, okay, now we're going to introduce friction into this thing. There's a couple of ways you can work C. One option is that you can go take the frictional force, which I gave you as -5 newtons, divide that by the mass, but this has to be the combined mass of everything, okay? Because that frictional force is now acting on both masses, okay? And then you can find your acceleration that way, okay? So you can go old school, force divided by mass equals acceleration, and then you can go V equals V naught plus AT, and then you know your acceleration, you know your initial velocity, and that final velocity is going to be 0, and then you can solve for time that way. Now, but here's what you have to be careful of. This initial velocity here has to be your answer from B, because this frictional force is kicking in after they move off together, okay? So this V naught has to be the initial velocity from B, not your initial velocity from A. Now, the other thing that you could do, okay, that's old school F equals ma. The other thing that you could do is go, oh, I like momentum. So you could go force times time equals change in momentum, which is mass times V minus V naught. So if you want to go kind of new age momentum, you can do this. Your final velocity is going to be 0. Your initial velocity is going to be from B. Use the combined mass. You know the force. Solve for the time that way. You do the exact same mass. You do the exact same math. All you do is just change the sequence. Okay? Because you're dividing by time. This gets you your acceleration. This is actually probably a little bit easier. But and then on D, you want to find the distance. And there's a couple of different ways you can do D. You could use that equation. You could use distance equals 1/2 V plus V naught times time. You could do distance equals 1/2 AT squared plus V naught time if you found the acceleration. There's a whole bunch of different ways you can do D, and I don't care how you do it. But here's the deal. So I've given you the answer for A, 3.13. On B, C, and D, all of those answers are going to be around 1 meter. Excuse me, not 1 meter. A numeric value of 1, okay, because they have different units. But all of your answers on B, C, and D are going to be around 1 meter, okay? All right, somebody had asked about 11. Okay. So on number 11, here's the deal. So you got Huey, Dewey, and Louie. Okay? And they're all at rest. Okay? They're just sitting there. So here's the whole kicker. They're just sitting there. So what's the initial momentum of the system? Caden, what's the initial momentum of the system?
0.
Why?
Well, they're all not moving.
Yeah, they have mass, they have inertia, there's just no momentum. So what that means is at any point after this, everything still has to add up to equal to 0, okay? Everything still has to add up to equal to 0. So here's what you've got. So I think Huey pushes Dewey if I remember right. So here's Huey, Dewey, Louie. So here's going to be this first interaction, okay? They're going to push off of each other. So the only way that works is if, because the momentum still has to add up to equal to 0, the only way that works is if those two values have equal and opposite signs, okay? So one's going to be like 5, the other one's going to be -5, okay? Whatever that's going to be. So what's going to happen is Huey here, he's going to start drifting in this direction. Huey's a goner. He's going to drift this way. Dewey is going to begin to drift towards Louie, okay? Now, on C, here's the deal. Everything still has to add up to equal to 0. So you've got this momentum going this way, right? then you're going to have the interaction between these two, and everything still has to add up to equal to 0. So if what could happen, here's an option, is that Dewey runs into Louis, he stops, and he transfers all of that momentum to Louis. So then Louis would have that positive momentum, which would make that balance out the momentum of Huey. Or they could push off of each other. Maybe one's going to be like positive 7, and the other one would be like negative 2, and then that would still add up to 5. That would balance out that negative 5. But here's the idea, is that no matter what happens, they still have to add up to equal to 0. So if you look at this from a vector standpoint, initially there was no vectors, okay? So that means afterwards, the sum of the vectors still has to be 0. So what you could do is you could draw, okay, after that initial reaction, here's the momentum of Huey, here's the momentum of Dewey, you're still going to end up back at 0. Then whatever you're going to have later on has to balance out that momentum vector of Huey. Okay? Cool with that. 4. Okay, so on number 4, let me use this handy dandy little setup that we did yesterday. Hopefully you all can see this. Okay, so this is what I talked about yesterday. So this polymer just hits and stops. This one hits and bounces back. So the one that hits and bounces back knocks the block over. The one that just hits and stops doesn't knock it over. So here's the deal. The changes in momentum have to be equal and opposite. So when this one hits and bounces back, that's a bigger change in momentum because it has to stop and then completely change direction. The one that embeds itself just hits and just stops, basically. So on a velocity time graph, the one that hits and bounces back goes from positive all the way down to negative. The one that hits and embeds just goes to some positive value. So this doesn't undergo as big a change in velocity. So it doesn't, the other one undergoes a bigger change in velocity. So it's a bigger change in momentum. So it exerts more force. Okay? Good with that. Okay? Anytime you hit and bounce, that's a bigger change in momentum. Okay, so on number 6, these all work the same way. You got the momentum of the bullet plus the momentum of the block equals the new momentum of the bullet. What, Miss Schertz? Hold on. I got to go help Miss Schertz with something. I'm going to be right back. Hold on. Oh. Okay, that crisis got averted. All right, so here's the deal. New momentum of the block. And if you shortcut this process, that's annoying. This is where you run into trouble. So on number 6, the whole key to this is that the bullet becomes embedded in the blocks. They're going to move off together. So over here, you can take the mass of the bullet plus the mass of the block times some new velocity. So in number 6, you know all of this. You know the mass of the bullet, you know the mass of the block, you know that they move off together. The initial momentum of the block is 0, that drops out. You know the mass of the bullet, the only thing you don't know is the initial velocity of the bullet. So in number 6, that velocity should be around 600 meters per second, which is about twice the speed of sound. Okay? You should have some negative answers on this assignment. If you don't have any negative answers, something's gone wrong. Now, Don't just go through and randomly put negative signs on numbers, okay? That's not going to work, all right? You have to have the numeric basis for them, okay? But I'm just telling you, some of these answers should be negative. All right. So I think I got through everything. 11, 10, 4, 6. Okay. Anything else for the good of the cause? We got everything answered. Life's good. Okay. All right. Fantastic. All right. So I have set out the lab, okay? And I'm going to show you what's going to happen with the lab and how we got the data, and then we'll go from there. So I'm going to move everything. I'm going to change the cameras so that they're over here. So hold on. This would be so much easier if you guys were here. Okay, you guys can see everything. Okay. All right, so this is even weirder because now I can't even see like the screen and see Caden, and so it's just going to get a little bit weird. Okay, so here's going to be the setup. So on your lab, okay, I've already given you the data. So the weight of the cart. So what I did is I took the cart, I hooked it up to a Newton scale, and the two carts are identical. So the two carts by themselves have a mass of 4.90 newtons. Now, on this data table, anytime there's an asterisk, okay, any space that has an asterisk, I want to see a calculation. So on this first one, what I'm going to call cart 1 is, I got cart 1, which is 4.90 newtons. I want to find the mass of cart 1. So all you're going to do is this is all you have to write down. Do not make this difficult. All you're going to have to write down is 4.90 newtons divided by G, which is going to be 0.50 kilograms. So this cart has a mass of 0.5 kilograms. Then I'm going to cart 1, I'm going to add a 0.5 kilogram mass to it. Okay, so that's going to be that setup, right? Okay, so imagine this. This is how this is going to play out. Then I'm going to have the other cart, okay, which is going to be this one, and it's going to have the exact same weight of 4.90 newtons, and we're going to have them like this. So here's the first thing, now that you've got the setup of what's going to happen on this lab. Let's talk about the pre-lab up here, now that you have a visual about what's going to happen in this lab. So on the pre-lab, we want a velocity time graph with motion of the cars at time 0, at which the plunger is released. Assume the cars have constant velocity after the impact of the plunger. Be sure to indicate which cart is the more massive one. So here's the deal. So what's going to happen is this. I want to get an idea of what's going to happen just in terms of the velocity time graphs. So let me show you what's going to take place. So I'm going to have it like this. I'm going to hit this, okay? And the carts are going to move away like this. So I've got both carts at 0. So imagine that. Let me get a piece of paper and draw. Hold on. That's easier to me than trying to describe this thing. Okay, good. All right, hopefully you all can see this. So here's going to be your velocity time graph, okay? So velocity time. So both carts are going to start at 0, 0. I'm going to hit the plunger and they're going to go in opposite directions. So what's going to happen is that you're going to have one cart. It has some action like this, okay? So this is when that plunger is expanding. This is when these carts are accelerating. This is when there's a force acting on it. This is when the momentum is changing. This is when it's accelerating, okay? Now, here's what you have to decide. So one of these is going to have more mass than the other one is, okay? So I don't care which one it is, but you need to make this sketch like on another sheet of paper. One of these is going to have more mass. Let's just say we're going to have the top one have more mass. Let's just say. So, but it has to have the same momentum as the one that has less mass. So the only way that, because that momentum has to be conserved, so the one with more mass is going to be moving slower, okay, so it won't accelerate as quickly. The one with less mass is going to be going faster. Now, notice that these are in opposite directions, okay? Now, the other thing that's going to happen is at this time, okay, when it's speeding up, when that plunger is expanding, that has to be the same for both, because one cart can't push on the other cart longer than the other cart pushes back. So, and this doesn't look like this, but how you should draw this is that after this happens, these lines should be parallel with your x-axis, because what we're assuming is that this system is frictionless, and that's going to be an important thing later on. So we're going to assume that this cart is frictionless. It's going to be moving along like this, okay? Then that velocity is constant, so the lines are going to be parallel. So on your pre-lab, so you would write, okay, hey, this is the one that has more mass. Okay, it's not going to be going as fast. The other one's going to be moving in the opposite direction. It's going to have less mass, but it's going to be going faster. So this is what this pre-lab graph should look like. Make sure that when these lines go parallel, that it happens at the same point in time. Don't have one go like this and then something like this, because that would mean that this one is speeding up a lot longer than this one is. So make sure that these lines, when they begin to flatten out, happen at the same point in time. Okay. All right. So that's the pre-lab. Now, in terms of data, okay? So what we've got to calculate is the velocity of the carts. So we're going to calculate the velocity of the carts after they begin to roll. So what I did, and the data that, how I set this up, is that we're going to push this in together, and on the initial position, this where it says position not, this third column over, notice that's the same at 0.78 meters. So what I did is that, and here's 0.78 meters, so I put both carts together at 0.78 meters. So I'm going to make this point right here the initial position for both of them. Now, this cart is going to be going in this direction, and this cart's going to be going in this direction. So I chose that point so that when I do this, okay, they both hit the edge of the track at the same time. So and that's going to be the whole key to this. So I'm going to have the starting position at 0.78 meters. There we go. I had that backwards. There we go. So I had it right there. So this cart's going to go, and it's going to go to this point. So the final position of this cart is going to be 1.06. So when this cart hits the edge, this right here is 1.06 meters. So it started at 0.78, and then it's going to end up at 1.06. So to get your displacement, remember displacement is position final minus position initial. So to get this displacement up here for cart 1, all you have to do is take 1.06 meters, where it ended up, and subtract 0.78 meters from it, where it started. Now, this cart is going to start at 0.78 meters, and it's going to go all the way down here, and then when it stops, the front edge of that is at 0.16 meters, okay, which is this point right here. So, with this one starts at 0.78, that ends up at 0.16. So remember, displacement is position final minus position initial. So on cart 2, you're going to take 0.16 and you're going to subtract 0.78 from it. That's how you're going to get a negative displacement. So this cart is going to end up with a positive displacement. This cart is going to end up with a negative displacement. Now, when you time it on how long it's going to take to roll, they both took the same amount of time of 1.28 seconds. So what I did is I set it up like this, okay? So they're both starting at 0.78. I've got a compressed spring, okay? When I hit it, it's going to come out. Mother Nature doesn't like potential energy, so it's going to convert that into kinetic energy. So I've got it like this, do this, point. And they're both going to hit the edge at the same time, and if you time it, that was 1.28 seconds. So, on that displacement, on the first one, you're going to have 1.06 minus 0.78, and that's going to get a positive displacement. On the second cart, you're going to take 0.16 minus 0.78, and that's going to get you a negative displacement. So, the key assumption that we're going to make in calculating the velocity is that we're going to assume that the velocity is going to remain constant. So we're going to assume that this is a frictionless surface. Obviously, if you try and do this lab with it upside down, it's not going to work so well, okay? Because then it's just going to come to a stop and you can't do anything. So this is why we assume that it's a frictionless surface. So, to get your final velocity, what you're going to do is you're going to take the displacement, one's going to be positive, one's going to be negative, and you're going to divide that by the time of 1.28 seconds, and that's how you're going to get your velocity. So let me give you a hint, okay? Your cart 1 velocity should be around 0.2 meters per second. Your cart 2 velocity should be around negative 0.5. Okay, so let me say that again. Your cart 1 velocity is around 0.2, and your cart 2 velocity is somewhere around negative 0.5. Okay, so that's going to tell you if you got those numbers kind of right. Now, change in velocity. Change in velocity is velocity final minus velocity initial. Do not make that calculation difficult. Basically, it's going to be that final velocity, which you just found, minus 0. That's all you have to write down, okay? It's not a difficult computation. Don't miss out on it. Those are the easiest points you were ever going to get in this class. Now, momentum. Obviously, the initial momentum of both carts is going to be 0. They're both at rest. We're not moving. Then you're going to calculate the momentum after they're rolling. That's the only one that's a little bit complicated. So for cart 1, you're going to take the total mass, which is 1 kilogram, multiply that by the velocity, that's going to be the momentum. Then you're going to take cart 2, the less massive one, 0.5, multiply it by its velocity, and that's how you're going to get that momentum. So if all goes well, on this column where it says momentum, your first momentum should be around 0.2. The other momentum for cart 2 should be around negative 0.2. So here's what you should get. Momentum of this one is about 0.2. The momentum of this one is about negative 0.2. Okay? Positive 0.2, negative 0.2. Change in momentum, momentum final minus momentum initial. Do not make this difficult. The initial momentum of both of those is going to be 0. Now, when you calculate the force, okay, this last column over here, this last column, read the instructions. I tell you to see question number 2. Question number 2 is down here. So on question number 2, I say, using force times time equals change in momentum and 0.02 seconds as the time, determine the force acting on each cart. So when you calculate the force, okay, you're going to use force times time equals change in momentum. Okay, so you're going to have force time equals change in your momentum. Okay, you're going to know you're changing your momentum. You found that already. This time, use 0.02 seconds. Don't use the 1.28 seconds that the carts are rolling, because the momentum isn't changing for the entire time. The momentum is only changing for as long as that spring is expanding. That's the only time that the momentum is changing. So it takes that long, 0.02 seconds. That's how long it took for that spring to expand. That's what you're going to use in that calculation. So if all goes well, okay, when you get all the way done, your cart 1 force should be around, or both of your forces should be around 10 to 12 newtons. One's going to be positive and one's going to be negative. So when you get done on this far column over here, both of those forces should be between 10 and 12. One's going to be positive, one's going to be negative. Okay? There you go. All right. Then you got a bunch of questions to answer down here. And let me move. I'm going to change everything back over here so I can draw on the board so you can actually see that. So let me change everything back over here. Oh, for the days that you kids are back in this classroom and life's going to be so much simpler. Okay. All right. So here's what's going to happen on the back side of the lab. So what's going to happen is that we're going to look at what's going to take place is that I'm going to take a block of wood like this. Can you all see me? Yeah. And I'm going to put that under this end that the more massive cart is going to roll towards. So I'm going to have it like this, okay? And then, this is tough to do and has to, still you guys see it, but you're going to get the idea. So imagine that I still have that other cart, okay? I'm going to hit the plunger. This cart's going to go up like this, and then it's going to start back down, okay? So it's going to go like this, and then it's going to change the direction. The second cart is just going to take off, and it's just going to roll straight down. So imagine this. I've still got the same situation. I'm still going to hit the plunger. This cart's going to go up, and it's going to come back down. This cart's going to start here, the less massive one, and it's just going to go, and it's just going to roll straight down like this. So on number 11, on that back side, I've given you this diagram. Okay? So here's positive, here's negative. Okay? So here's what I want you to see. So this cart up here, okay, when you look at this, what's happening, this little bit here, again, this is when this plunger is going to expand, right? Now, here's what I want you to think through. Riley Wirtz, okay? Riley Wirtz, are you with me? Okay. Can you see the cart?
Yeah.
Okay. So this is the cart that's going up the hill. Okay, you ready? So I'm going to hit the plunger and it's going to go like this, and then it's going to come back down. So does the cart change direction, Riley?
Yes.
Yes. Okay. So as soon as that plunger leaves, what does it begin to do?
Accelerate.
Is that acceleration making it speed up or slow down? No. So here I am. I'm going to hit the plunger and it's going to do this. Okay? So as soon as that plunger leaves, what does it begin to do?
Slow down.
Then it's going to come to a stop, and then what's it going to do? Speed up, right? So the top cart slows down, and then it speeds up. Okay? Now, it works. The bottom cart, what's it going to do? It's only going to speed up. Okay? Now, these are both on the same incline. Okay? So, because they're both on the same incline, and this is going to be important, that means that the accelerations of both of these are going to be the same. So listen to me. When you think through what's going to happen on number 11, if you're on a frictionless surface, and I'll go through the math if you want, but the shortcut way to calculate acceleration, I don't see that. Oh, hold on.
Mr. Burkamp.
Yep.
Is this number 11 on the lab? Or what are you talking about, number 11?
Hold on, I might have misspoke. I'm sorry, it's number 8 on the lab. I don't know how I got number 11. It's number 8.
Gotcha.
I for some reason I had this was number 11 in my mind. It's number 8. Okay? My bad. It's number 8. Okay. So an acceleration on an inclined plane without friction is A equals G sine theta. Mass is not a factor. So because they're both on the same incline, they're both going to have the same acceleration. You don't have to calculate it, but just realize that they're both going to have the same acceleration. So the acceleration going up is going to be the same as the acceleration going down for both carts. So here's what you want to think through. So this is this one that's going up the hill, okay? So this is when the plunger leaves. So one of 3 things can happen to this graph. It's either going to slope up like this, and it's going to keep speeding up going up the hill. It's going to be a horizontal line, meaning that it's not going to accelerate at all, or it's going to slope down like this, okay? That's what's going to happen. So this is the one that's going up the hill. So either, and this is when the plunger quits expanding. So it's either going to go up, it's going to be horizontal, or it's going to go down like this. Now, this is the one that's going down the hill, okay? So this one's going to be like this, boom, that's going to expand, and this is going to go like this. So again, one of 3 things can happen at this point. It's either going to slope up, it's going to be a horizontal line, or it's going to slope down like this, okay? That's what you have to decide. So there's 3 things that could happen here. Slopes up, slopes parallel, slopes down. This one slopes up, slopes parallel, slopes down, okay? That's what you want to think through. Okay. Now, on the application questions, those you answer on a complete other sheet of paper. Do not try and answer any of these questions 1 through 4 on this sheet of paper. Nothing. You can answer the lab questions up to like number 10, but when you get through these last 4 questions, I want them done on a completely separate sheet of paper. I do not want anything written here, okay? I want everything done on another sheet of paper because there's no way you're going to have enough room to do that. Pay attention to some of these problems where if they're moving in opposite directions, remember that means their velocities are going to have opposite signs, okay? So keep that in mind. when you get to question number 2, don't be afraid if you have the same numeric answer again and again and again. The signs might be different. So on number 2, don't be surprised if you get the same numeric answer more than once. Okay? Just saying. Anyway, so I am done. So if you've looked over the lab, is there anything else you want me to clarify on the lab? You got all the data. So here's the deal. I'm done. So there's like 10 minutes left. I'm going to stay zoomed in. If you want to start working on this lab, and then, hey, if you have some questions while you're working on the lab, that's cool. You can ask me, and I can go over them. So if you look ahead and you go, wow, I have no idea how to do this question, this would be the time to ask. It's a little preemptive thing. So I'm done. So if you want to zoom out, you can zoom out. Don't forget your clothing orders are due by Friday. Okay? So Friday's that deadline by like the end of the day. So even if you don't have the money, but I just need to get the order in. Okay? So even if you just say, hey, I'm not going to get paid till next week, go ahead and submit your order, and then you can give me the money later on. Okay? But I at least want the orders by the end of the day on Friday. So, okay. All right. I'm done.